Have you ever wondered why golf balls look like tiny planets covered in craters? Those dimples aren't just for decoration. They're actually one of the most elegant solutions in sports engineering. And the story behind them involves physics, drag, and a principle called turbulent flow that completely revolutionized how we understand movement through air. If you're curious about the hidden forces that shape everyday objects, stick around and subscribe to the channel. We break down the science behind things you see all the time, but never really think about. Let's start with a fundamental question. What happens when an object moves through air? When anything travels through a fluid, whether that's air or water, it experiences resistance. We call this drag, and it's the force that opposes motion. Imagine you're sitting in a car with your hand out the window. When you tilt your hand, you feel the air pushing against it. That's drag in action. For a golf ball, drag is the enemy. It slows the ball down, reduces distance, and makes the sport less interesting. So golf ball manufacturers have spent over a century trying to minimize it. Now, here's where it gets interesting. In the 1800s, golfers noticed something peculiar. Old golf balls that had been used and roughed up actually flew farther and more predictably than smooth new ones. This observation seemed backwards. Surely a smooth surface would cut through the air more easily, right? Wrong. The rough surface was actually helping the ball travel farther. And nobody really understood why until scientists started studying aerodynamics more carefully. To understand dimples, you need to know about two different types of airflow: laminar flow and turbulent flow. Laminar flow is smooth and orderly. Air particles move in parallel layers, like a calm river. When air flows laminarly around a smooth sphere, it creates a wake, a zone of low pressure behind the object. This low pressure zone acts like a vacuum, pulling the object backward. That's a huge source of drag, and it's exactly what you want to avoid. Turbulent flow is chaotic and swirling. Air particles move in all directions, mixing and colliding. When air flows turbulently around an object, something magical happens. The chaotic motion near the surface actually helps keep the air attached to the object longer. This reduces the size of that troublesome wake behind it. Smaller wake means less pressure drag pulling the ball backward. And here's the key insight. Dimples force the air to become turbulent. They trip the boundary layer, the thin film of air right at the ball's surface, and turn it from laminar to turbulent. Let me explain what happens in more detail. When air first approaches a smooth golf ball, it flows laminarly. As it moves around the curve of the ball, the flow is stable and organized. But smooth surfaces create separation. The air literally peels away from the ball's surface, creating that large, inefficient wake. With dimples, something different occurs. Each tiny depression acts like a little turbulator. As the air encounters these dimples, it gets disturbed and starts mixing. This turbulent boundary layer clings to the ball's surface much more stubbornly than smooth air would. The boundary layer stays attached longer as it travels around the ball, which shrinks the wake significantly. The result is counterintuitive but powerful. A dimpled ball experiences less total drag than a smooth ball, even though the dimples add surface area. You might think more surface area would mean more friction and more drag. That's true for something called skin friction drag, which does increase with dimples. But the reduction in pressure drag from the smaller wake more than compensates. The net effect is lower total drag. This is why a professional golf ball can fly over 200 yards, while a smooth ball of the same size and weight might only travel 150 yards. But wait, there's even more complexity. The size, shape, and depth of dimples matter enormously. Manufacturers have invested huge amounts of research into optimizing these parameters. If dimples are too shallow, they don't disturb the air enough. If they're too deep, they create too much skin friction drag. There's a sweet spot, a perfect balance where the reduction in pressure drag is maximized while skin friction drag remains reasonable. Different manufacturers have found slightly different optima, which is why you'll see variation in dimple patterns across different golf ball brands. The speed of the ball also affects how dimples perform. At low speeds, the boundary layer doesn't transition to turbulence as easily, so dimples are less effective. At high speeds, like those produced by a professional golfer's swing, dimples work brilliantly. This is part of why professional golfers hit the ball so much farther than recreational players. They generate the speeds necessary to fully activate the aerodynamic benefits of dimple design. A slower swing means the flow patterns around the ball don't develop the same way. The Reynolds number, a dimensionless quantity that physicists use to characterize flow patterns, is crucial here. It compares inertial forces to viscous forces. For golf balls in flight, the Reynolds number is high, meaning inertial forces dominate. At these high Reynolds numbers, turbulent flow is the natural state, and dimples help initiate and maintain this turbulence right at the ball's surface. Engineers have used computational fluid dynamics and wind tunnel testing to refine dimple designs, adjusting everything from pattern geometry to distribution across the ball's surface. Here's something that really shows how important this is. The discovery of dimple aerodynamics revolutionized not just golf, but many other sports and engineering applications. Tennis balls have a fuzzy surface that serves a similar function. It creates turbulence. Even baseballs and softballs have seams that help with aerodynamic effects. The principles are universal. Whenever you need an object to move efficiently through air, you're dealing with these same fundamental forces. Scientists have also discovered that dimples affect more than just drag. They influence lift and stability too. The chaotic flow patterns created by dimples can produce lift forces that make the ball curve in flight. Professional golfers exploit this by adding spin to their shots, which interacts with the dimple-induced turbulence to create the hooks, slices, and curves that make golf so tactically interesting. Like this video if you're impressed by how much physics is packed into something as simple as a golf ball. The history of dimple optimization is a fascinating arms race. In the early 1900s, as golfers noticed the benefits of roughened surfaces, manufacturers started intentionally adding patterns. Early dimples were random and uneven. Over decades, through experimentation and eventually computational modeling, designers created more sophisticated patterns. Some balls have shallower dimples near the poles and deeper ones near the equator. Others use hexagonal patterns inspired by honeycomb structures. Each design represents thousands of hours of testing and refinement. Modern golf ball design involves scanning actual flight trajectories, analyzing high-speed camera footage, and running thousands of simulations. Equipment manufacturers test their products against competitors in controlled environments and real-world conditions. The investment is enormous because even tiny improvements in aerodynamic efficiency translate to distance and consistency, which directly affect professional tournament outcomes and consumer satisfaction. But here's the beautiful part. All of this complexity emerged from a simple observation. Old, worn golf balls flew better than new, smooth ones. Someone asked why. Scientists investigated, engineers experimented, and we discovered fundamental principles about fluid dynamics that apply far beyond golf. The dimple story is really a story about how observing nature, asking questions, and rigorously testing hypotheses leads to innovation and deeper understanding. If you want to understand the world around you better, subscribe to the channel for more videos diving deep into the science behind everyday objects and phenomena. What's your experience with golf balls? Have you noticed a difference in performance between different brands or conditions? Drop a comment below and let me know what you've observed. Thanks for watching, and I'll see you in the next one.